welcome to this session. So, we will continue our discussion on unit testing. We are saying that in unit testing, each unit is tested independently of the other units. So, what it really means is that if a unit needs to be called from some other unit and also it calls some other units, then since we have to test it independently, we need to write small software here called as the drivers and stubs. A driver is one which simulates the behavior of the function or the unit that calls this unit and possibly supplies some data to the unit being tested. Whereas, the stub, it simulates the behavior of a function that has not yet been written or it is not available. So, we are testing this unit independent of the other unit, and therefore, we use a stub here which simulates the behavior of the other unit. Possibly, we have just stored some values here that if 2 is called, this other unit is called with a data 2, then it returns the data 11 or something. So, maybe just a lookup. So, these are very simple software, the driver and stub, and these simulate the behavior of the other units, because testing this unit in isolation. This just explains that a little bit. So, this is the unit, and then the stub is the one which this unit needs to call, and the stub we have written here for some sample data. We look up for if a data it is called with some value, just looks up the result here and returns that. Whereas, a driver, it not only calls the procedure under test, that is the unit, it possibly might have other global data and so on, which might this procedure might need. The unit might need some global variables and so on, the driver would have that. Now, let us have a small quiz. We know the unit testing, at least what is its purpose. Now, what do you think? Would unit testing be a validation activity or a verification activity? We had actually discussed this issue some time back, that whether unit testing will be a verification activity or a validation activity. Actually, the answer is that unit testing will be a verification activity. It is not a validation activity, because validation means we are testing the working of the entire system with respect to the requirement specification. Whereas, in unit testing, we are testing only one of the functions or unit with respect to the design. So, the high level design or the detailed design, the detailed design will have the specification for this unit. So, we are checking during unit testing whether the code is written in conformance with the detailed design, and therefore, unit testing is a verification activity. Now, let us see how do we design test cases for unit testing. There are essentially 3 main approaches for designing test cases. One is black box approach, white box approach, and gray box approach. The black box approach, as the name says, we don't have we don't need to look at the code of the unit. We just look at the input output behavior of the unit, that is the specification, detailed specification, where we will have this unit, what does it do, given a data, what data does it, what result does it produce, and then we have this white box testing, where we actually have to look at the code. we look at the code to design the test cases based on whether some code elements are getting covered, decisions, conditions, statements and so on. The third one is a gray box approach, where we look at the design of the unit and we come up with the test cases. So, in a black box, we just look at the input output behavior and come up with the test case. In white box, we look at the code and based on the source code, we design the test cases. In gray box, we do not look at the input output specification, neither the white box, the code, we just look at the design of that and based on that we come up with the test cases. First, let us look at the black box approach. In the black box approach, the software is actually the unit that we are considering is considered as a black box. We do not know how the code has been written, we just know what are the input that it takes and what are the output it produces. So, this is also called as the functional specification of the software. So, the test cases are designed here looking at the functional specification, we do not need to look at the code, and for this reason the black box testing is also called as functional testing. But before we look at the black box testing strategies, let us answer a very basic question, that what is hard about this black box testing? We know the input data, know the output result that is to be produced. So, what is hard about this? The hard about this black box testing is very hard, because typically for a practical software, the data for a unit will be extremely large, the data domain. So, testing with respect to all elements of the data domain will be very difficult. And not only that, it might take unit might take multiple parameters, and each parameter will have its data space. And when we do testing, we will not only have to consider the data values that are taken by each parameter, but also we have to check the different combinations of the different parameters. So, just having a parameter taking all values is not enough. We will have to check for each value of one parameter what are the result when all other values for the other parameter are considered. So, that is the combinations of the values for different parameters. So, this is a hard problem, not only even if it takes one parameter, number of test cases can be very large, and then typically you will have to consider multiple parameters. Just to elaborate the problem, we will take a very simple example, that is we have written a very simple code, takes two integers as argument. Our unit here is a function, name of the function is check equal, taking two integer set parameters and then returns 0 if they are not equal and returns 1 if they are equal. So, very trivial function, and we are trying to test it. But then if we want to test exhaustively whether it works for all possible values of x and y, we will have to consider how many values are, what is the domain size for x and y. So, the domain size for x, assuming a 64-bit computer, is 2 to the power 64, and similarly for y is 2 to the power 64, and then we have to consider all possible combinations of these two parameters, and therefore, it becomes 2 to the power 128, and then if we really test with this data value 2 to the power 128, let us just for our curiosity check how long it will take. If we take 10 seconds, key in it very fast each value, pair of value, to take a billion year to enter all possible values. But then you might say that why not automatically generate all these possible values and let the computer execute. So, that also will take long time to generate all possible values, because each execution takes finite time and it will keep on running for a long time. And not only that, such automatic testing has its own problem, because if the result is produced, we do not know whether it is the correct result. So, only thing that we can detect is a crash. So, anyway, but what we really wanted to point out here is that the hard thing about black box testing is that the number of possible data items are extremely large. So, our objective in test case design is to design a set of test cases which should be as effective as testing with all possible values, but we should use a minimum number of test cases. So, how do we do that? The main idea in black box testing, we will look at several black box testing techniques, but one thing that is common to all these is that we construct a model of the domain, because the data domain is very large. We can't really test it effectively by looking at the domain itself, other than taking all possible values. So, we construct a model, and then this model we call as the domain model, and based on this domain model we select test data from this model. So, that is the main idea here. Now, based on that, let us see how do we design the test cases. Okay, before that, let us have one basic idea about white box testing. White box testing, we look at the code, and based on that we know what is the internal structure of the software, and therefore, the white box testing is called as the structural testing. Now, let us look at the black box testing and how do we design test cases, what are the different strategies available for designing the black box test cases. So, black box test case, as we are saying, we just look at the input output behavior, we know what will be the input corresponding output, and system we do not have any knowledge about that, appears like a black box to it, and therefore, it is also called as input output driven testing or data driven testing. So, our goal in test case design is to achieve the thoroughness of exhaustive input testing with as little number of test cases as possible. There are many black box test strategies that exist: scenario coverage, equivalence partitioning, special value testing, boundary value testing, cause effect testing, combinatorial testing, orthogonal array testing, and so on. So, let us look at these techniques. First, let us look at the equivalence class testing. In equivalence class testing, we need to construct a model of the domain called as the equivalence partitions. So, we partition the input domain to equivalence classes. The idea is that the partitioning is done such that, so we will partition the data, input data, into a number of classes, such that each class will be, when you consider value from any class, the result will be the same as considering any other value from the same class. So, the program behaves in a similar way for every input value belonging to an equivalence class. So, when we consider, we have developed the equivalence classes. For any equivalence class, all the values are equivalent to the other values, in the sense that checking the software with any one value is as good as checking with all other values of that class. So, if you are doing a scenario based testing, in scenario based testing is very simple, where we just execute each scenario of the software. So, for let us say book return example, the scenarios can be that the book was returned successfully. Another scenario can be there is somebody who had reserved the book, and therefore, the book return could not be done. So, whether it could not, it was really that it could not be done when somebody else had reserved. So, that is a scenario. A third scenario, maybe the membership of the member had expired, and when renewing it said that the membership has expired, cannot renew the book, please return the book. So, whether this scenario is correctly implemented. So, in scenario based testing, the requirement specification document typically documents all possible scenarios of operation of various functionalities, and in scenario based testing we just write test cases to execute each scenario. So, in equivalence partitioning, obviously each scenario is a different equivalence class. So, this says that if we know the scenarios, know the specification for this unit, and we know what are the scenarios for this, then we will have as many equivalence classes, at least as many equivalence classes as there are scenarios of operation for this unit. Of course, there will be more equivalence classes. Let us look at those. So, the premise of equivalence class testing is that the input domain we are partitioning into different equivalence classes. So, this input domain is partitioned into 3 equivalence classes, and the main premise is that if we take any one value from this equivalence class, that should test the system as good as any other value taken from the same class. So, for equivalence testing we just consider one value. So, what is the logic behind this assumption that any value is as good as any other value? The assumption is the basis for this assumption is that once one feature, the software is exercised with one of these test data, it executes certain elements, and all other elements are executing the same set of program elements, and therefore, we will observe if it's a success for one, then it will be also success for all other. If it is a failure for this, and there will be failure for all other. So, the main assumption here is that any one element here will be exercising the same set of program elements as any other data here. Now, the hardest problem here in equivalence partitioning is that given a unit and its input output description, how do we design the equivalence classes? So, one thing is we identify the scenarios, we examine the input data, we examine the output that might be produced for different data, and then based on that we design the equivalence classes. So, we can have few guidelines about how to design the equivalence class partitions. One is that if a input data is specified by a range of values that it can take between 0 to 1000 or something, then we have one valid and two invalid equivalence classes. If it specifies a specific number of test data, then we have one valid and one invalid equivalence class. If it is input is a boolean, then we have one valid and one invalid equivalence class. For example, let us say the area code for a telephone number is value between 10,000 and 90,000. So, what will be the equivalence classes? So, there will be three equivalence classes, two invalid less than 10,000, more than 30,000, sorry 90,000, and valid equivalence class between 10,000 and 90,000. Similarly, we might have password 6 character string. So, here also we will have one equivalence class which is less than 6 characters, and another equivalence class which is exactly 6 characters, and third equivalence class which is more than 6 characters. Now, let us look at some examples based on what we discussed and see if we can identify the equivalence classes, and later we will have some practice also given, so that you can test whether you can have practice designing equivalence classes, and depending on the unit that under test, it can be very challenging to design the equivalence classes. Let us look to start with, let us look at a very simple problem. Our unit or a function takes 3 integers denoting 3 sides of a triangle. Now, our function just writes down the type of the triangle, whether it is isosceles, scalene, equilateral. So, our function that we have written takes 3 integers and then prints out or displays what is the type of the triangle, whether it is isosceles, scalene, equilateral, not a triangle, and so on. So, how do we design test cases? We do a scenario coverage, that is the first thing. Just see here that these are the different scenarios of operation. In one scenario, it writes down isosceles, another scenario scalene, third scenario equilateral, fourth scenario not a triangle, and so on. So, we must have test data, equivalence classes defined corresponding to isosceles, scalene, equilateral, not a triangle, because different elements of the program are exercised when we declare, where the function declares the 3 sides to be isosceles, scalene, or equilateral. So, we just take one value from here, one value from here, one from here. So, these are, once we have the equivalence classes corresponding to this, we have those values. So, the main idea here is that the first level in the equivalence class, we have 2 sets of values that we design, 2 sets of equivalence classes, 2 equivalence classes here, 2 sets actually, the valid set of equivalence classes and the invalid set of equivalence classes. So, first we have 2 here, valid, invalid, and for each of these we design, we look for further equivalence classes in the valid. So, these are set of valid equivalence classes and these are set of the invalid equivalence classes, and then once we have done the equivalence partitioning, we found out all the valid equivalence classes and all the invalid equivalence classes, we just pick one value from each of them randomly, and this will form our equivalence class test suite. So, we will stop here and we will continue from this point in the next session. Thank you.